Okay, so as we are extending your tool set for constructing differentially private algorithms, I'll speak now about composition. I'll speak more about composition. Already you heard about it yesterday from Katrina. And you may notice already that there is a new concept on the slide, the privacy budget. We haven't spoken about budget yet, but it hints that we'll treat privacy in a way that is similar to, I don't know, other resources and that we can use only to some extent, and hence we have to be careful on how we actually manage this resource. Okay, so a few important properties of differential privacy. We already spoke about post-processing. We know that if an algorithm is differentially private, then also if you apply something on another algorithm on the outcome, this is also differentially private and it preserves the parameters. Composition, we'll speak about today. Adaptive executions of differentially private mechanism, and this emphasis on adaptiveness, we'll explain it later. And this also results in differential privacy. We can think about post-processing as a special case of composition when the second algorithm does not get to touch the data, it only sees the outcome of the first algorithm. And you could ask, why do we care about composition? And I should tell you that it became like a very major, like a very central research to differential privacy to understand what happens when we compose differentially private algorithms. Why do we care? One is for privacy. It's an important property of differential privacy that it composes. Otherwise, you could produce several seemingly privacy-preserving computations, but together, when you compose the results, privacy will be breached. We don't want that to happen, so it feels that this is like an essential property of a good privacy definition, and we're happy we have it for differential privacy. Furthermore, we mentioned already that differential privacy is, in a sense, is a programmable framework for constructing algorithms. And it's important for us when we design algorithms that we can think in a more modular way, that we can build algorithms for complex problems from algorithms for the simpler problems. And if we have composition properties, then we can do that. And furthermore, we'll see tomorrow that, or actually on Wednesday, that sometimes we care about composition for other reasons. Even if privacy is not our goal, sometimes differential privacy can prove a useful tool. Suppose you are doing research about fish. It turns out that if you give fish privacy, you can benefit from that, and we'll try to make sense of this. Let me remind you the basic composition thing. The setting is that we have several differentially private computations, MI, each is epsilon I, delta I, differentially private, and then if we construct from them a larger computation that applies these T differentially private computations with independent randomness, then the result is that this is some of the epsilon i's, some of the delta i's differentially private. Okay? I'll call that basic composition. And already this suggests that if we have a goal, we want to have a certain epsilon and delta overall, and we use computations that utilize hopefully smaller values of epsilon and delta, we have to do that carefully. We have to manage the way in which we use up these quantities. Okay, it's because otherwise we may be deviating from our privacy goal. So this is why we're talking about these, especially about epsilon, as a kind of a privacy budget. The privacy parameter gives us a budget that we can use throughout our computation on smaller computations. Okay? So we want to split our privacy budget into smaller quantities, and we want to do it carefully and smartly. And what we'll do in this session, we'll look at two things. First, we'll examine one example of, that shows, in a sense, how to be careful about using your epsilons and doing it right. And then we'll speak about composition theorems. Okay, and in particular, we'll see that there are more refined theorems than this basic composition theorem, that they are more efficient in the way that they use the privacy budget, in particular advanced composition and the optimal composition theorems. Okay, so let's look at this problem. Suppose, which is related to a concept that Katrina spoke about in the morning. Suppose we want to answer all threshold queries. Okay, so let's see what is. The data comes from an order domain, say values between 1 and t. Okay, and the database is just a collection of elements from this order domain. We want to approximately answer all the queries of the form, how many points have value between 1 and small t, okay, or the fraction of points that have this value, okay? We could look, we already have some tools. We could compute the global sensitivity of such a query. It's 1 over n, it's an easy calculation. And maybe we could think about answering, if we want to answer all the queries, we have t, little t such queries, we could answer all of them by adding noise Laplace 1 over epsilon prime, where we have to cut epsilon prime. We will divide epsilon by t and use basic composition, and then we're fine. But the problem with this solution is that the noise magnitude that we'll be getting is really huge, because noise is now going to be of magnitude about t over epsilon. Okay? Can we do that with smaller noise? So just as an example, suppose this is our data set, and here we have 15 points if I did my counting correctly, and this query Q7 returns 7 over 15, because if you count the number of points that have value 7 or lower, I think there are 7 such points. Okay. So we'll try to do it more efficiently, and the algorithm I want to present is algorithm that is based on a tree construction. I'll use a binary tree, although if you want to really optimize the noise level, you may want to have a larger RET, but this only affects the constant, so I will not care about that now. And here's, I impose the binary tree over the range, so let's think about t as a power of 2. And I also, can you see all the edges in here? I barely see them, but they're pretty thin, yeah. But in every node, I counted the number of points that are in a leaf that is a descendant of that node, okay? So overall, you see that there are 15 points here and so on. Now, suppose we're interested in this Q7. How many points do we see there? So one way is to add up the number in the leaves, but we can also do it differently. We can go along the path and identify these nodes. Each is a node in a different depth in the tree. And if we add up these numbers, we get the right answer. Okay, so if we could compute the counts for these internal nodes, then we have an alternative way of computing these sums. Okay, so we'll try to use that to get a smarter way of using our privacy budget. So what do we have here? Suppose we are interested in computing these values. How many points fall in each of these leaves? What kind of computation is that? We've seen this before. Sorry? Histogram. It's a histogram, yeah, because we are splitting the domain into disjoint subsets, okay, and we're counting how many points fall in each of these subsets. And similarly, for this level of the tree, and so on. So we see that we can actually compute here a small number of histograms, And do you remember the noise level we have to add in a histogram? What's the sensitivity of histogram? Just like to refresh our... So it's 1, and so we have to add noise 1 over epsilon, depending on the neighborhood relationship that you want to define. It's either 1 or 2. So we add relatively low noise in a histogram. It does, in particular, it does not depend on the size of the domain. So we have here log t histograms, in each we add noise that is roughly 1 over epsilon. And this would give us a more efficient way of using our privacy budget. So let's see what we're getting. So I'm still using basic composition with the basic theorems that I will introduce later on. You can optimize this a little further, but let's stay there with the basic composition. So we can compute log t histograms, which means if we use basic composition, we have to divide our epsilon into log t smaller values. Each is epsilon over log t. Okay. And then we add noise, Laplace noise proportional to epsilon over log t to each count. The noise variance is logarithmic now. And each answer to threshold query now is sum of at most log t values like that, because we're summing values, one value from each histogram. So we're getting that the overall noise variance is this thing. It's logarithmic in t. And the noise magnitude that we'll get overall is logarithmic in t. So we, instead of getting noise that is linear or polynomial in t, like root t or third root of t, you could think about ways to also to get that. We're getting a significantly lower noise magnitude here. Okay, and the trick was to use. We are using basic composition, but we're using it in a better, smarter way. Okay. Now, another application for the same idea is online counting. Suppose now that we don't have our data set to begin with, think about a case where we have a polling booth. At each time unit, somebody comes and votes, either 1 or 0. Okay, so these are, sorry. So the values appear in time. So, where are the values? Here. The first one, second one, and so on. And after each value appears, we want to approximate the count so far, like how many people voted 1. Okay, we want to do that over time. So observe that computing that is the same as computing threshold, all threshold queries, just that we want to do that in an online fashion. So like in the previous slide, we got all the data beforehand and we computed these histograms. Now we want to do that in an online version. After the ith person comes in, we want to output a number which is an estimate of the total count so far. Okay? So we can do that. And one question to think of is how to adjust the definition of differential privacy to this online setting. I'm not going to get there, but this is certainly an interesting question. You can look in these papers. But here's a simple technical observation. If we want to use the previous technique, we need to find these nodes that we add up to get the count, the answer to the threshold query. But note that nodes fill up before we need to use them. I think I have that here. Let's see. Here, we only need the first leaf in order to answer this, but it already is filled up. Now, after we see the second point, we only need actually that red point on like depth, one less than the leaves, but it's already filled up and so on. Now, we need to add up. Do I have a laser printer here? A laser pointer?
Yeah, it does. Yeah, that's
Or what should I press?
Kobbi.
Yeah.
Forward button.
Okay, thanks. So we only need these two values, but these nodes are filled. And once the node is filled, we can filled up. We can only then add the Laplace noise to get the noisy count in that node. So the point is that we can maintain this. Actually, we only need to maintain nodes along a path. Those nodes that needs to be updated, and nodes that we're still using for our computation, but everything else we don't have to maintain. So we can also do it with relatively small memory, only about log t counts. Okay, so that was one tool, and it has a few applications in algorithms. I'm not sure what we'll actually be able to show throughout the week, but it is used in several places. Okay, let me continue now to speak about composition, and I want to focus on advanced composition, the theorem that is known as advanced composition. So, and from here I'm using a lot slides by Guy Rothblum. So how to define composition, okay? And we want to define it in the strongest way. Think about somebody who's composing algorithms. Now this guy, although it may be that this guy is the designer of an algorithm, but maybe this guy is somebody who's issuing queries to our data, asking for us to perform a computation and so on. This guy is our adversary, okay? So the adversary want to prove privacy with respect to quite a strong adversary. So the adversary will be able to choose both the database. Okay, this is usually not what is happening in the real world, but we want because we want to consider a strong adversary, the adversary will be able to choose the databases. It will be able to choose the algorithms that we apply to the data. And furthermore, will allow the adversary to make these choices in an adaptive way, in the sense that the adversary will first see answers to first queries, and then choose databases to apply the next analysis and the specific analysis, okay? The only thing that I'm not letting the adversary choose yet is the value for epsilon delta. I will assume that the value for epsilon delta is fixed and chosen ahead of time, okay? So let me show you this thing in the picture. The adversary will begin by choosing two databases and a mechanism, differentially private mechanism. Okay, so this is very similar to the definition of differential privacy that we've seen. In that definition, the adversary chooses two neighboring databases and a mechanism, and now we have to show that the distributions, the outcome distributions of applying the mechanism on these two different databases are very similar. Okay, so this will be sent here to a challenger, and the challenger will choose one of these databases, okay? We could think about it, maybe if B is 0, this is the real world database in a sense, and if B is 1, is the database with my data removed or changed, okay? So the adversary then sees the output of the computation on the first database, it chooses the second database, sees the outcome, and the mechanism, and so on. At the kth time, he chooses the kth neighboring databases x0k and x1k, the kth mechanism mk, and gets the answer. And now what you want to require is that the views of the adversary are in a sense very similar, that regardless of the choice of this bit B, the distributions are similar. Okay, so this is going to be our definition. Note again that this is a very, very strong. The adversary does not have to make all the choices beforehand. It only does them, makes these choices in an adaptive way. So we're giving the adversary quite a lot of power here. So I will not be able to get into all the details of how one analyzes this game, but I want to speak about the main ideas. Okay? And one important concept is, how do we measure a notion of privacy loss in the context of differential privacy? And I want to say that this parameter epsilon is the parameter that measures the privacy loss. This is what we're interested in. So look at this. Let's choose two neighboring data sets, x0 and x1, and then apply M on x0 and draw some outcome C. Okay? We can ask, is C, this outcome, more likely to be the outcome when we apply M on x0 than when we apply on x1? Because we applied M on x0, we expect to see outcomes that are more likely for x0 more often than to see outcomes that are more likely for x1. Okay? And in a sense, differential privacy requires that, although this happens, that the difference in the probabilities that we're going to see such outcomes, the advantage to one side, like to seeing an outcome that is more likely on M0, is not that large. Let me look at this concept again here. Suppose we have these two probability distributions on outcomes. The red one is for x0, and the blue one is for x1. You see that they are very similar, so there is a chance that this preserves differential privacy. And now, suppose we see the outcome 19, okay? In this case, the blue line is above the red line, so it's more likely to see 19 as output on x0 than on x1, and similarly, with 40, this is, it's the other way, okay? You can also ask how likely, or is, to compare how likely it is on x0 and x1, and so let's look first at the ratio between these probabilities, okay? So we see an outcome, we ask what is the probability that we will see it under x0, and when we apply M to x1, this is the likelihood ratio. When we took the log, we're getting something that is, this is our epsilon in differential privacy. This is what we're bounding, okay? So let's define that to be the privacy loss of a specific outcome C. You can think about this as if an adversary sees C, in a sense, this measures how more confident is the adversary that the input was x0 when he considers that it could be either x0 or x1. Okay. So this is the log of likelihood ratio. And with epsilon 0, with pure differential privacy, we get that with probability 1 over the randomness of the mechanism M, the loss is bounded between minus epsilon and epsilon. Okay? So we don't allow this ratio to be greater than epsilon, than e to the epsilon. And with epsilon delta, differential privacy, and the star is that this is not exactly the definition, but it's good enough for our discussion. It's almost equivalent. With epsilon delta, we get that this happens with high probability, with probability 1 minus delta, at least 1 minus delta. Okay, so with probability delta, something bad could happen, that the ratio could be large, but otherwise the ratio is bounded by e to the epsilon, so the loss is bounded between minus epsilon and epsilon. Okay? So let's see this in a graph. So what we're seeing here is the cumulative distribution function of the loss. So for just an example, for epsilon differential privacy, it's always between -1 and 1. So here the cumulative distribution is, the probability is 0, and here it's 1. But with delta, epsilon delta differential privacy, it might be that sometimes we deviate, and in this case, so this is minus epsilon and epsilon. This is for the case epsilon equals 1. With epsilon delta, it might be that sometimes it's larger than epsilon. But the overall probability that this happens is bounded by delta. Okay, so I just copied the definition of this loss here. And let's think on what happens when we have multiple executions of differentially private computation, okay? So think about that adversary. At the beginning, he has no clue whether this bit B is 0 or 1, okay? But then he begins to see outcomes of computations that are differentially private, and the adversary begins to build his confidence whether this bit was 0 or 1. In a sense, differential privacy requires us to make sure that this confidence will not grow too much. And this is expressed in the loss function. But when we perform multiple independent executions of these computations, the loss accumulates. In the worst case, the loss could accumulate additively all the time, okay? But maybe sometimes we'll be lucky and that will not happen, okay? And this is exactly what we'll try to use. So in the worst case, we know that this loss is bounded and it's at most epsilon. And let's think about the case where M is epsilon differentially private with delta equals 0. So the loss is at most epsilon. In the worst case, we could incur a loss of epsilon in every time we execute a differentially private mechanism, okay? And that was the basis for our basic composition theorem. We said that even if that happens, we're only losing something linear. Our loss is linear in the number of executions, okay? So if we perform this, if we perform T computations that are epsilon differentially private, we lose at most T times epsilon in privacy. So that would be the worst case. But this may be pessimistic because the loss can be positive or it can be negative, and maybe we get some cancellations. So maybe we're not doing this linear number of steps to one direction, but we're going left and right, so it takes time until we accumulate a significant loss, okay? And to analyze how you can benefit from this, we can think about loss now as a random variable, okay? We can analyze its mean, we can analyze how it progresses, and you may begin at some point, but you see, it's not necessary that it goes linearly to the right all the time. Sometimes it goes to the left, sometimes to the right. It shouldn't jump up and down as it does in my slide, but I hope you see the point. So we did a lot of steps here, but we didn't get that far because there were a lot of cancellations. And if that happens with high probability, and we're getting into the details of this behavior only with small probability, maybe we can swallow that with our delta parameter and get a better composition theorem. So that's our intuition. So one way to think about this is that, in a sense, the challenger communicates a bit, his bit B to the adversary, but the way he communicates the bit is very noisy, okay? the channel is defined by this game. First, the adversary chooses these two databases and a mechanism M1, and he gets a noisy version of that bit, which is M applied to X, B, and so on and so forth. Okay? So this is the rule. In each round of this protocol, something about B is communicated, but it's quite noisy because these are differentially private computations. So it turns out that to understand how this thing behaves, that was a beautiful observation in this work of Kairouz and Vishwanath, and later used in a work by Mutag and Vadan, that it's enough to understand how randomized response composes. Okay? And let's see what happens when we use randomized response. So here I rewrote randomized response in this way. Let me pass it out. We're given a bit X, okay? And the answer is X with probability e to the epsilon over e to the epsilon plus 1. We negate X and return that as an answer with probability 1 over e to the epsilon plus 1. So I know it may be confusing. Yesterday you were asked to toss 2 coins in your head to do this, and that gave us epsilon ln 3, I believe. This is a more general recipe for the same thing. Let's look at the loss function, okay? In this case, remember the loss was the probability of seeing the outcome given that the input was X, divided by probability of seeing the other outcome given that the input was, divided by the probability of seeing the same outcome given that the input was not X. So in this case, the loss is epsilon because we have the ratio between e to the epsilon and 1 here. And in the second case, the loss is minus epsilon because it's 1 over e to the epsilon. When we take the log, it's minus epsilon. Okay, so we're making the largest steps possible here. So that's bad for us. That's bad for privacy. But on the other hand, look at what happens here. If epsilon is small, then e to the epsilon is very close to 1 plus epsilon. So these two probabilities look like very close to 1/2. So with the probability about 1/2, we're going in the positive direction, and with probability about 1/2, we're going in the negative direction. So we expect that overall we'll stay roughly around 0. And actually, what will happen is that if we're making t steps, then we expect to be in distance about root t from the origin, okay? Let's do it slightly more carefully. First, let's look at the expected loss. It's not exactly 0 because the probabilities are not equal. There is a preference, a small preference to giving the right answer, okay? And if you do the calculation, let me do it slowly. So here, with this probability, the loss is epsilon, and with this probability, the loss is minus epsilon. Then when you plug things in, you get this. Now I replaced epsilon with 1 plus epsilon, assuming it's a small number, and we're getting that the expected loss is rather tiny. If epsilon is a small number, epsilon squared is definitely a small number, okay? So in expectation, we're only losing epsilon square in terms of our privacy budget in every step. So this, if we're thinking about applying this t times, so linearity of expectation would say that our behavior, the expectation is going to be linear in that instead of being linear in epsilon. Okay, so instead of spending t times epsilon instead of incurring loss t times epsilon, we'll incur in expectation loss t times epsilon squared, a lot less. And usually this is going to be the less dominant term in the loss. So the loss random variable is has expectation about epsilon squared. Loss is always bounded by epsilon, and now think about this random walk that I had with a point jumping to the right and to the left there. We can analyze it. It's very similar to a martingale. You can modify it a little by, you can make the expected loss 0 by subtracting epsilon squared. And hence, we can use Azuma's inequality to bound how we deviate from the expectations. Okay, and overall, you get something like that. You need to choose the parameter T accordingly to get the best bound. And what you get is that if we begin with a mechanism M that is epsilon differentially private with delta equals 0, and we execute it k times, then we're getting the loss, or our new epsilon, is going to look like k times epsilon squared. That's from the constant drift that we have in each, may have in each application. But the crucial point is that here we're getting a factor of root k times log 1 over delta, a factor that stands in front of the epsilon instead of k times epsilon. Okay, so this is where we gain. Let me check the time. Until when is this? 20 more minutes?
20 more minutes, yeah.
Okay, sure. So, let me restate that again. The theorem, if we compose k pure differentially private algorithms, each is differentially private with parameter epsilon 0, then this is our epsilon. And notice that we have this parameter delta G here. In a sense, we can get various results depending on our choice for delta. Okay? You choose a delta, this delta G. Okay? So that's a probability that the loss will deviate from this bound. And once you chose delta G, you get this factor in front of the epsilon 0. Okay? Compare this with the basic composition where we lost something that is linear in K. And it's important. And one example is we spoke about performing count queries. With this way, we can answer n count queries with error that goes, that grows proportionally to root n. Okay, just using independent Laplace noise or using Gaussian noise, and this is almost tight when you compare it with the reconstruction attacks that John talked about earlier. Now you can also have a similar analysis in the case that the algorithms we use are not pure differentially private algorithms, but they have a non-zero delta. And so if you compose k algorithms that are epsilon 0, delta 0 differentially private, you get something that is similar. What's important to note is that delta here grows linearly in k. So again, we have this parameter that we can choose here, similar to lambda g here, okay? And the resulting delta parameter is this parameter here plus k times delta 0. In a sense, we have to incur this linear dependency on delta 0 because we're performing these algorithms k times. Each has a probability delta of a privacy disaster, and so these probabilities have to accumulate. So in the last part of the talk, I want to speak about a variant of differential privacy that we did not present yet, and probably won't have a lot of time to talk about, but this is certainly bringing you to some of the things that happen now in research. Before I do that, the optimal differential privacy, the optimal composition theorem. Sorry, so I'll get there in a minute. So in the result, in the advanced composition result that I mentioned, all the epsilons and all the deltas were the same, okay? We're composing mechanisms that all have the same privacy parameters. What would happen if we compose mechanisms that have different epsilons and deltas? And what we want to get is the best theorem that we can prove for in this general case, which means we're looking for a best worst case result. It doesn't mean that every time you will compose mechanism, you will get that loss in privacy. But this is the best that we can prove generally. Okay, that's the overall, this is the result that works over all choices of mechanisms, databases, and events. Okay. There have been a couple of papers here. One is a paper by Karuz, Song, and Vishwanath, where they consider the case where all the epsilons are the same and all the deltas are the same, but they give tight bounds, which improve on the bounds we get from the advanced composition theorem that I mentioned, that I described. Asymptotically, it gives the same result, but the improvement can have practical significance. And then Murtag and Vadan showed a similar bound for the general case, where the epsilons and delta can vary between mechanisms. And they also show, interestingly, that computing this epsilon g is a computationally hard problem. Computing it exactly disappeared in TCC last year, but you can approximate it quite well in polynomial time. Okay, and now I'll say a few words about concentrated differential privacy. So let's look at this loss variable again. Differential privacy requires that either this loss parameter is bounded by between minus epsilon and epsilon, or bounded with high probability, but maybe we can relax that a little. Let's only require that this is concentrated, okay? That it's not too wild in a sense, okay? So we want that in expectation the loss will be small, and also that the loss will be concentrated around the expectation, okay? So I'll follow the formulation by Dwork and Rothblum. There's a more recent work by Ban and Steinke that gives alternative definitions and in some cases simpler analysis. Okay, so if we look at the same picture we looked at before, so we've seen the green and blue lines. Here we will not require this containment between -1 and 1, minus epsilon and epsilon, to be so strict. It will be smoother, but we will still require that this is concentrated around, in this case, around 0. Okay? So we want that the privacy loss would be a random variable that looks no worse than a normal random variable, concentrated around mu with variance tau squared. And so this is our requirement for the expectation, and we require that it will not have heavy tails. We want this to be sub-Gaussian, okay? So the probability of deviating from the expectation goes down like exponential in the squared deviation. Okay? It maintains many advantages of differential privacy. For instance, because Gaussians, when you add up Gaussians, you get a Gaussian. It's really easy to get a composition theorem here. So we get that both the expectation and the variance add up. Okay, so you're getting, in a sense, exactly what we got in the advanced composition theorem, but it's much easier to get that. Okay. It also handles linkage or auxiliary data in a similar way to differential privacy. It has some more properties. It's a relaxed notion of privacy in the sense that if we execute if we have just one execution of a differentially private algorithm, then the chances of us falling in this outside the region minus epsilon to epsilon are not that small, okay? But if you compose many studies, then we expect to be very concentrated. In a sense, when in that case, we're not losing anything beyond what we had with the usual differential privacy definition, okay? Let's compare benefits in accuracy. So suppose we answer k sum queries where epsilon equals 1 with epsilon 0 differential privacy. There we only have the basic composition theorem. We insist on delta being 0. So the privacy parameter adds up linearly, so we get noise that is linear in the number of queries that we ask. With epsilon delta differential privacy, we improve that to something that goes like root k instead of k, but there is this factor that depends on the delta parameter. And with concentrated differential privacy, we can get rid of this dependence on the delta parameter, which again, if we think about practical applications, this can be significant because we want delta to be a relatively small number. Okay, and then again, I mentioned that this is roughly tight because of the reconstruction attacks that John mentioned. This is just a picture to compare what happens when we compose these things. So suppose we compose as many computations. You see that the red line, in a sense, almost matches what we get with epsilon differential privacy. So this is what we expect to get, like in the result of the privacy loss that we have if we execute many differentially private, if we execute many computations, the overall privacy loss is going to be very similar whether we begin with epsilon differential privacy or with concentrated differential privacy. Okay, let me summarize, and then maybe we have a few. I want to stress again that adaptive composition is important for privacy. It's part of having a reasonable definition of privacy is that we need composition, and we need that composition to be the composition theorems to be as strong as possible. In particular, we want to encounter adaptive adversaries. I think for people who do cryptography, this is probably much more natural than for people who are just thinking about analysis. It's important that we have composition so we can design complex algorithms, and I think you will see more and more complex algorithms as we go on, and as I mentioned also for data analysis. One way I think about this is we have all these interesting, wonderful tools for building differentially private algorithms with less and less noise, okay? We spoke about randomized response, global sensitivity, and there are other frameworks As you see, this is quite rich by now. But this by itself wouldn't be sufficient because in many cases it's not easy to construct algorithms just relying on these basic constructions. What we have with composition and what else? With post-processing is a way to steer all these tools together in a pot and get much more interesting algorithms and for a really large class of tasks. Okay, I think that was said and that was said. Yep, I'll stop here.